Okay, so in today's lecture, we're going to be discussing chapter 6, which is chemical reactions. So first off, when we look at chemical reactions, let's first start by reviewing and discussing chemical equations. So fundamentally, a chemical reaction involves making and breaking bonds, or the transfer of electrons between atoms and molecules. Now, there are a few laws that govern chemical reactions, the first of which is the law of conservation of mass, which states atoms cannot be created or destroyed in chemical reactions. The number of atoms of each element does not change before and after a reaction. So for example, if we look at hydrogen peroxide decomposing to yield water and oxygen gas, we notice on the left-hand side we have 4 hydrogens and 4 oxygens. On the right-hand side we have 4 hydrogens and 4 oxygens. The number of atoms of each element does not change before and after a chemical reaction. The connectivity of those atoms does change. Now, since atoms have mass, the number of atoms of each element remains constant. The total mass before and after a reaction does not change. So we've seen this a lot in combustion reactions. So if we take sodium solid, for example, and react it, let's do calcium instead. And we react it with oxygen, we'd end up generating calcium oxide. So if we start with 80 grams of calcium, and we react it with 32 grams of oxygen, in the end, at the end of this chemical reaction, we would get 112 grams of product. So the mass before and after a chemical reaction does not change. We can use conservation of mass to solve for the mass of one of our reactants in a chemical reaction. Now, there's one other rider that I need to talk about, which is this statement that the total number of subatomic particles does not change during a chemical reaction. Okay, so this primarily concerns protons, neutrons, and electrons. So just like atoms are conserved, particles are conserved. This primarily applies to electrons, where electrons can move between atoms and molecules, but the number of electrons total in a chemical reaction does not change. This primarily comes up for reactions that involve the transfer of electrons, known as redox reactions. Any questions so far on this review? Okay, so let's continue elaborating on this idea. So chemical equations describe the conversion of reactants to products, okay? So the reactants, these are the species that are reacting in your chemical reaction. These are found on the left-hand side of the chemical equation. The products are the molecules produced from this chemical reaction, and the products are found on the right-hand side. In terms of major features of a chemical equation, the reaction arrow indicates the reactant and product sides of the chemical equation and indicates the transformation of reactants to products. Additionally, there's other information contained in the chemical equation. So as you notice, each of our compounds and elements in this chemical equation has a symbol after it. This symbol is known as the state symbol, and it indicates the physical state of each substance. S for solid, L for liquid, G for gas, AQ for aqueous, where aqueous is very specific and it means that it's dissolved in water. We've seen these state symbols before, and we're quite familiar with how to assign them to different elements. So now you may also notice in our chemical equation we have a series of numbers. So these numbers are very important in this chapter, and they're known as the reaction coefficient. They indicate the number of each molecule, atom, compound, etc., participating in the chemical reaction. Now, there's no such thing as half an atom. There's no such thing as half a molecule. Those statements don't have any physical meaning. So it's really important to note that your reaction coefficients must be a whole number. They must show whole numbers of atoms and molecules reacting. So what do we mean by whole number? No fractions. Okay, so let's keep going with this idea. So there are a few symbols that will show up above the reaction arrow. So for example, in some chemical reactions, you may see a chemical formula above your reaction arrow. So for example, this is a chemical formula of a species, and anytime you see a formula above the reaction arrow, that indicates that you have a catalyst. Now, what is a catalyst? It's a chemical component that accelerates the rate of forward and reverse reaction. So it dramatically increases the rate. We actually saw this in laboratory where we decomposed hydrogen peroxide using yeast, where the catalase enzyme in yeast served as our catalyst. In this case, our catalyst is iodide anion. This is sort of a problem if you're ever trying to ship hydrogen peroxide via sea. If you happen to expose the hydrogen peroxide to seawater, it could pretty rapidly decompose. So catalysts are not reactants or products. They are neither consumed nor produced by the chemical reaction. So a catalyst simply accelerates the rate of reaction, but is neither produced nor consumed. So it's not a reactant or a product. It's neither. Now, the other major symbol that you'd see above the reaction arrow is this delta symbol. Now, what does this delta symbol mean? Well, this delta symbol indicates that heat is added. Some reactions require heat in order to initiate the reaction. You may also see a temperature where they say a temperature higher or lower than room temperature for that chemical reaction. Okay, so those are some symbols and those are some pieces of information that you'll see in various chemical reactions. Let's talk next about really the cornerstone of this chapter, which is balancing chemical equations. Well, the first rule that's going to govern there are three general rules that govern our process for balancing chemical equations. First, a balanced chemical equation has the same number of atoms of each element before and after the reaction. So for example, if we have sodium solid reacting with chlorine gas, we generate 2 molecules of sodium chloride solid. On the left-hand side, we have 2 sodium and 2 chlorine. On the right-hand side, we have 2 sodium and 2 chlorine. So as we can clearly see, we have the same number of atoms of each element before and after our reaction. Now, another rule is molecules and atoms react in whole number ratios. So your reaction coefficients must be whole numbers. So for example, looking at the above equation, we have 2 sodium atoms reacting with 1 molecule of chlorine. We typically don't write the coefficient of 1, but I'm just making it explicit just so that way everyone can see that we have a whole number of chlorine molecules, and we get out 2 sodium chloride molecules. So again, molecules and atoms react in whole number ratios. And as a final rule, just like in our chemical formula, how the subscript must be the smallest possible set of whole numbers, the reaction coefficients must be the smallest possible set of whole numbers. So let's give an example. Let's give an example. So if we have H2O leads to H2 plus O2. So let's say we have 4H2O leads to 4H2 plus 2O2. Are our coefficients the smallest possible? Can we simplify our coefficients? So we have 4 to 4 to 2. Are these coefficients the smallest possible ratio? Are these the smallest possible set of whole numbers? No. So what's a simpler ratio? Instead of 4 to 4 to 2, it should be what? Instead of 4 to 4 to 2, it should be 2 to 2 to 1. Exactly. So writing out our modified equation, we have 2H2O leads to 2H2 plus O2. And this would be a proper balanced chemical equation with the smallest possible set of reaction coefficients. Okay, so let's talk about the process behind balancing chemical equations. So first, you write an unbalanced basic chemical equation with the correct formula and physical states. Then we count the number of atoms of each element in the reactants and products. So let's suppose, just as we're working through an example, let's suppose if we're working through an example, we're given the problem aluminum solid plus chlorine gas leads to aluminum chloride. Okay, so in terms of our process for solving and generally balancing this equation, our first order of business is to count the number of atoms of each element. So if we're making a tally, I see 1 aluminum atom, I see 2 chlorine atoms, I see 1 aluminum atom and 3 chlorine atoms in my product. Again, we count our atoms by looking at our subscripts and our reaction coefficient, which we haven't put in yet. Now, as a general rule, you balance atoms mentioned only once on each side first by adjusting the reaction coefficients. Now, this is really important, and you really need to be careful about this. You cannot change the chemical formula when you're balancing an equation. You can only change the reaction coefficient, the number in front. So in this case, the way that I like to think about this is I compare the atoms mentioned on the left and the right-hand side. I see we have the same number of aluminum atoms, so we have no issue there. For chlorine, we have different numbers of chlorine atoms. We'll talk more about the idea behind why we're choosing certain coefficients. But in order to balance chlorine, we need to find the smallest common number of atoms between 2 and 3. So we'll use what is known as the least common multiple method, where we just simply take the number of atoms on each side and multiply it by the number of atoms on the opposite side. So at the end of this process, we have 6 chlorine atoms and 6 chlorine atoms. And in order to finish off balancing this equation, now that we have 2 aluminum atoms on the right, we put 2 aluminum atoms on the left. We'll talk more about the mechanics behind balancing a chemical equation and in terms of counting atoms in detail. In general, you write out your chemical formulas, you count your atoms of each element, and then you adjust your coefficients. Once you've adjusted your coefficients, you then check to make sure that your chemical equation is in fact balanced by ensuring that there are equal numbers of atoms of each element on the left and right hand side. So on the left, we have 2 aluminum and 6 chlorine. On the right, we have 2 aluminum and 6 chlorine atoms. So this is a nice little cliff notes of what we're going to be doing throughout this chapter. And what I'm next going to show you are a method and a series of procedures that you can use to balance chemical equations and count atoms efficiently. So this is just a general overview of what is the process for balancing a chemical equation. Now let's go into detail onto alternative methods. And let's work through an example following each step of this procedure, and how would I want you to show your work, and how would I recommend that you go about balancing these simple chemical equations that don't have a unique aspect to them. So let's do an example together. We're asked to balance the following chemical equation. So we have iron and oxygen reacting to yield the following iron oxide species. Okay, so the first step is already done for us. We won't have to worry about it for later. So we have iron solid plus O2 gas leads to Fe3O4 solid. Okay, so now that I have my equation, let me just write that equation over here. Now what I'm going to do is I'm going to count the atoms of each element on the left and right hand side. And I'm going to make my tally in columns. So how many iron atoms do I have? How many iron atoms do I have in iron solid? How many iron atoms do I have? How many iron atoms do I have? How many iron atoms do we see in Fe solid? Just one, right? We see how many oxygen atoms in O2. How many oxygen atoms do we see in O2? 2, yep. And in Fe3O4, we have how many iron atoms? In Fe3O4, how many iron atoms do we have? 3, yep. And we have 4 oxygen atoms. Perfect. So we've counted the number of atoms of each element. And what we're next going to do is we're going to identify each element with different numbers of atoms in the reactant and product. Okay, so looking at our equation, we see that iron is not balanced and oxygen is not balanced. They have different numbers of atoms of that element. Perfect. So we've completed our preliminary view of this chemical equation. Let's now talk about what do we do next? Well, you balance atoms mentioned only once on each side first by adjusting the reaction coefficients. Okay. So, again, as a refresher, we have iron and oxygen unbalanced. We have 1 iron on the left. We have 2 oxygens on the left. and we have 3 irons and 4 oxygens on the right. So I like to play a little bit of a guessing game here. And I try to guess what reaction coefficient would give me the same number of atoms on each side. So 1 iron atom times what would give me the 3 iron atoms on the right? 1 times what would give me 3? What reaction coefficient should I guess? What reaction coefficient should I guess?
3.
1 times what gives me 3? Yep. Okay, perfect. Again, to calculate the number of atoms, you take your formula, you look at the number of atoms indicated by the subscript, and then you multiply it by your reaction coefficient. Good, good. Now playing another game, we have 2 oxygen atoms. 2 times what would give me the 4 oxygen atoms found on the right-hand side? What coefficient should I guess? 2 times what would give me 4?
2.
2, yep. Perfect. So now we have equal number of atoms of each element on each side of our chemical equation. I find this guess and check method is quite useful. So in the end, we have the following equation. And we can check, we have 3 iron and 4 oxygens on the left. We have 3 iron and 4 oxygens on the right. So this equation is completely balanced. So if you're dealing with a more complicated chemical equation, just as a refresher, to revise your count, you multiply the number of each atom by the reaction coefficient. We relist the total number of atoms of each element, and we repeat adjusting our coefficients until all of our elements are balanced. Does this process make sense to everyone so far? Does this process make sense to everyone so far? Any questions on this example? So if we don't have any questions, what we're going to do is we're going to focus on applying this skill to balance a chemical equation. So I'd like you to take a look at the following chemical equation, and I'd like you to balance the following chemical equation. So you may want to rewrite this just so that we have a little more space to work with. And don't be shy to submit your responses via the chat or verbally, and we'll discuss this example in about 3 to 4 minutes. The Canvas quizzes for you to reattempt and recheck your understanding of the lecture material for this chapter will be up later tonight. And I already see some reasonable responses in the chat. Let's keep working through this problem and we'll discuss in about another 3 minutes. And don't be shy if you have any questions to ask them via the chat or verbally. And don't be shy to submit your responses in the chat or unmute and propose your responses verbally. And we'll discuss in about another 2 minutes. And the coefficients I see in the chat so far look good. We'll discuss in about another minute to a minute and a half. Let's try to get a few more responses in the chat. And if there are any questions during this problem, don't hesitate to ask. Let's try to get at least or another 2 to 3 responses in the chat, and we'll discuss in about another minute. And if you're having trouble balancing, don't be shy to ask a question for any aspect of these problems. Okay, so let's discuss this example. So first and foremost, we need to do a tally of the atoms of each element that we have. So first and foremost, in C6H6, we have 6 carbons and 6 hydrogens. Okay, in bromine, we have 2 bromine atoms. In C6H4Br2, we have 6 carbons, 2 hydrogens, and 2 bromines. And in HBr, we have 1 hydrogen and 1 bromine. Okay, so let's just go through and let's check and identify which elements are unbalanced. So carbon, we're good to go. Same number of atoms of each element on each side. So that should be a 4. Sorry about that. Okay. Now looking at bromine, I have 2 bromines on the left. I have 3 bromines on the right. So bromine, we still need to balance. Hydrogen, I have 6 hydrogens on the left and 1 hydrogen on the right. So the quizzes for this chapter will be posted later tonight to answer that question in the chat. So now that we see that hydrogen and bromine are not balanced, let's adjust the coefficient in the molecule that has the least number of atoms or that contains an atom that's mentioned in the least number of compounds. So carbon's balanced, so there's no point in us modifying C6H4Br2. That's pointless. If we adjust its coefficients, we'll unbalance carbon. So we can't really change the number of bromines on the right-hand side unless we go and we adjust the coefficient of something on the right-hand side. So my question to all of you is, 1 times what would give us the 2 hydrogens that we need, and 1 times what would give us the 2 bromines that we need? What should we plug in for our coefficient in front of HBr? What coefficient do we need? 2, exactly right. So now, in total, we have 6 hydrogens, 6 carbons, and 4 bromines on the left. And we have 6 carbons, 6 hydrogens, and 2 bromines. Okay, so we still have some work to do. So in our revised count now, bromine is not balanced. So let's repeat this process. 2 times what would give us 4 bromines? 2 times what would give us 4 bromines? What should we plug in for the coefficient of bromine?
2.
Yep. Perfect. So now we have 6 carbons, 6 hydrogens. Oh, yep. And 4 bromines. So let's rewrite our balanced equation one more time. So we have C6H6 liquid plus 2 Br2 liquid leads to C6H4 Br2 liquid plus 2 HBr. Perfect. So now we have a balanced equation. Just to check our work, we have 6 carbons, 6 hydrogens, and 4 bromines. We have 6 carbons, 2 hydrogens, and 2 bromines in our first compound. And we have another 2 hydrogens and 2 bromines in our second compound. Adding it together, we have 6 hydrogens and 4 bromines. So our equation is completely balanced, so we put a check mark next to it. So we've effectively balanced this equation. So you just count the number of atoms, adjust the coefficient, and keep adjusting your coefficients until you have a balanced equation. Does that make sense to everyone? Any questions on this example? If not, let's do some more examples. And I'd like you now to try and attempt the following problem. And I'd like you to try to balance the following chemical equation. And don't be shy to submit your proposed responses in the chat or unmute and submit your proposed responses verbally. We'll take about 3 to 4 minutes to work through this problem, and then we'll discuss together as a group. Yeah, there's a small typo. Let me correct that. Should be H2O. Yep. Yep. Thank you for pointing that out. So let's try to balance the following equation, and then we'll discuss in about another 3 to 4 minutes. If you're curious what type of reaction this could be classified as an acid-base or a double displacement or double replacement reaction. We already see some reasonable responses in the chat. Let's spend another 3 minutes on this problem and we'll discuss. And the responses I'm seeing so far look perfect. Let's spend another 2.5 minutes on this problem and then we'll discuss momentarily. And if you'd like me to provide feedback on your response, don't be shy to send a message into our general or private Zoom chat, and I'll be happy to provide feedback. And if there are any questions at all, don't hesitate to ask. And please don't be shy to submit your responses, and we'll discuss this example in about another minute to a minute and a half. Okay, so let's discuss this example. First and foremost, let's make a tally. So we have 1 aluminum atom, 3 oxygen atoms, and 3 hydrogen atoms in aluminum hydroxide. We have 1 hydrogen and 1 chlorine atom in hydrochloric acid. We have 1 aluminum atom and 3 chlorine atoms in aluminum chloride. And we have 2 hydrogens and 1 oxygen atom in water. Okay, so now looking at elements that are not balanced, well, almost all of them aren't balanced. I see chlorine, I see hydrogen. I'll have to be a little careful with hydrogen, and I see oxygen. So let's focus on balancing the elements that are found in the least number of compounds first. So which element do we want to start with? Which element do we want to start with? Anyone have a preference? Which element do we want to balance first? Aluminum, sure, but aluminum is a pretty straightforward one. It's already balanced. We have the same number of atoms on each side, but it's always good to check. So yep, we completed aluminum. Now what element do we want to balance? What's the next one on our priority list? What element shows up in the least number of compounds? What element shows up in the least number of compounds? Chlorine, sure. That's perfectly reasonable to try and balance. Okay, so we have 3 chlorines on the right. In order to get our chlorine atoms to match, I'd like us to ask the question, 1 times what would give us 3 chlorines? What coefficient do we guess? 1 times what would give us 3? Okay, so yes, we'd plug in a coefficient of 3. That would give us 3 chlorines and 3 hydrogens. Okay, so now chlorine is balanced. Hydrogen is still a problem, however. But let's leave hydrogen alone for now, because we have another element that's not balanced that's found in less compounds. So looking at oxygen, we have 3 oxygens on the left and water only has 1 on the right. So 1 times what would give us 3 oxygens? What coefficient should we plug in, or should we guess, for water? 1 times what would give us 3? 3, yep. So plugging in our coefficient of 3, we now have 6 hydrogens and 3 oxygens. 6 hydrogens on the left, 6 hydrogens on the right. Everything looks balanced to me. Just to check, I'm going to rewrite my equation, and I'm going to check that I have the same number of atoms of each element on each side of my chemical equation. So just to check for our reference, we have 1 aluminum, 3 oxygens, and 3 hydrogens. I have 3 hydrogens and 3 chlorines. So these hydrogens add together to give us 6 hydrogens total. In aluminum chloride, I have 1 aluminum and 3 chlorines. And in water, I have 6 hydrogens and 3 oxygens. So 6 hydrogens, 3 oxygens, 3 chlorines, and 1 aluminum. So everything is balanced. So this equation is completely balanced. You'll slowly develop the ability to balance equations extremely quickly over the course of this chapter as you continue to practice. I always like to introduce this very procedural method just so that way when you're dealing with a very complex chemical equation, it becomes easier to manage. Now, there's another way that I like to balance chemical equations. There's another way that I like to balance chemical equations, and it's known as the table method. So let's do an example considering we have the following chemical equation at play. So in the table method, following our step-by-step procedure, we're going to write an unbalanced chemical equation with the correct formulas and physical states. That's already provided for us, but this one sentence is going to give us a lot of grief in later parts of this chapter. You're going to really need to make sure your nomenclature skills are solid as we move through and we prepare for the second half of this chapter. So with that said, we're just like always going to count the number of atoms of each element in the reactants and products. And then we're going to count the total number of atoms of each element in the reactants and products. Okay, so let's see what it looks like in practice. So I like to make a table for each reactant. So I plug in my reactants. So I have phosphoric acid and sodium sulfide. So just to do a count, I have 3 hydrogens, 1 phosphorus, and 4 oxygen atoms. In sodium sulfide, I have 2 sodiums and 1 sulfur. Okay. And you can make like a very clear dividing line if you want between reactants and products, if that helps you visualize it a little bit easier. So for our products, we have hydrogen sulfide and sodium phosphate. I wouldn't want to run this reaction near anyone because it will smell terrible. Hydrogen sulfide smells like rotten eggs. Anyway, counting our atoms, we have 2 hydrogens and 1 sulfur. In sodium phosphate, we have 3 sodiums, 1 phosphorus, and 4 oxygens. I'm going to touch on this idea later, but whenever you have ionic reactions, you can also think about balancing equations in terms of ions. So this lump of 1 phosphorus and 4 oxygen atoms is our phosphate ion. We'll touch more on that later. Okay, so now that we have our counts established, what we're going to do is we're going to identify the elements with a different number of atoms on each side. So what elements are not balanced? What elements are not balanced? Sodium, yep. And hydrogen, okay. So there is a very quick trick to balance these types of ionic equations or exchange-like reactions. Looking if we have different numbers of atoms of each element on each side, what you're going to do is you're going to take the number of atoms on the left-hand side and plug it in for your coefficient on the right-hand side. You're going to take the number of atoms on the right and plug it in for the coefficient on the left. This is known as the least common multiple method. So we plug in a coefficient of 2 for phosphoric acid and 3 for hydrogen sulfide. Now you may say, does this actually work? Well, in the end, we generate 6 hydrogen atoms, 2 phosphorus atoms, and 8 oxygen atoms. On the right-hand side, we have 6 hydrogen atoms and 3 sulfur atoms. So hydrogen, we've done a wonderful job of balancing it at the cost of throwing a wrench into our other balanced elements. Now, looking, we see now that phosphorus, so I'm going to put a circle around them. So now that we see we've unbalanced phosphorus and oxygen, okay, and sulfur is not balanced. So it seems like we just made a bigger mess, but we can break this down piece by piece. So let's move on to balance sulfur. So I have 3 sulfurs on the right. So 1 times what would give me 3 sulfurs? 1 times what would give me 3? What coefficient do I plug in for sodium sulfide? One times what would give me 3? 3, yep. So we plug in a coefficient of 3 for sodium sulfide, and that in turn gives us 6 sodiums and 3 sulfurs. So at least sulfur is now balanced. So I can take that off the list of problems I have to deal with. Now, let's look. We have 6 sodiums on the left. We have 3 sodiums on the right. So 3 times what would give us 6 sodiums? What coefficient should we guess? What coefficient should we guess? 3 times what would give us 6? 2. And that 2 applies to all of our atom counts for this compound. So that gives us 2 phosphoruses and 4 oxygens. So now going through and checking our work for this balanced equation. So we put in the following coefficients. And we see phosphorus is now balanced. Sodium is now balanced. All of our atoms are now balanced. So let's rewrite. So we've done this entire procedure in one table. There's additional space provided if we want to break this process down into each of its component steps. So let's take this moment, and now that we've done a bunch of coefficient adjustment, let's write out our revised balanced equation. Let's write out our revised balanced equation with all of the coefficients that we've carefully calculated and created. So just as a check to make sure that this equation is in fact balanced. So sodium sulfide, we have 2 sodiums and 1 sulfur, has a reaction coefficient of 3. So we have 6 sodiums and 3 sulfur atoms. Phosphoric acid, we have 3 hydrogens, 1 phosphorus, and 4 oxygens. We have a coefficient of 2. So we have 6 hydrogens, 2 phosphoruses, and 8 oxygens. Hydrogen sulfide, we have 2 hydrogens and 1 sulfur. Our reaction coefficient of 3 gives us 6 hydrogens and 3 sulfurs. Finally, sodium phosphate has 3 sodiums, 1 phosphorus, and 4 oxygen. Has a coefficient of 2 to give us 6 sodiums, 2 phosphorus, and 8 oxygen. So as we can clearly see, this full equation is balanced. The one thing I like about the table method is that it makes the calculations a little bit more straightforward. And just as a summary of, once again, a trick for balancing these types of exchange reactions where we have different number of atoms of each element on each side, you look at the number of atoms of each element. So in this case, we have 2 sodium and 3 sodium, and you cross the number of atoms into the subscript. So this is known as the least common multiple method, and it's very powerful for balancing ionic equations. So, does this example make sense to everyone? Is everyone comfortable with this example? If not, let's try to apply our problem-solving skills to another problem. So I'd like you to try and balance the following equation, and we can write this equation again just to give everyone a little bit more space to work with. And I'll give everyone about 4 to 5 minutes to balance this equation, and then we'll discuss this example as a group. Don't be shy to submit your responses for your proposed balanced chemical equation in the chat or verbally. And if you have any questions at all, don't hesitate to ask them in the chat or unmute and ask your questions verbally. I provided a table for you in the notes to attempt to balance this equation. And I've rewritten the chemical equation above, so that way it's a little bit closer. So we'll discuss this example in about 3 to 4 minutes. And if there are any questions or any proposed responses, don't be shy to submit them via the chat as a public or private message. And we're already starting to see some reasonable responses in the chat. Let's spend a little bit more time on this problem and then we'll discuss. And it's really encouraging so far to see all the responses from students in the chat. Let's spend another 3 minutes working through this problem and then we'll discuss. And if you don't like using the table method, you don't have to. I just find it helps make this idea of counting atoms and adjusting coefficients a little more explicit. And once you've seen this explicit reasoning, you can start to integrate that when you solve future problems. So if you know how to do all the steps, you can start to take shortcuts. And we'll discuss this example in about another 2 minutes. Really don't hesitate to submit your proposed responses in the chat, and I'll be happy to provide feedback. Really want to give everyone time to work through and generate their own solution to these problems. And then we'll discuss this example momentarily. Yeah, and the responses I'm seeing so far in this chat look great so far. Okay, so let's discuss this example. So I'm going to use the table method just because we have a table convenient, and I always like showing off these processes. So in the following compound, we have 2 hydrogens, 1 silicon, and 2 chlorines. Okay. In water, we have 2 hydrogens and 1 oxygen. Okay. In our products, we have H8Si4O4. We have 8 hydrogens, 4 silicons, and 4 oxygens. For our reaction coefficient, we're not going to worry about that just yet. For hydrochloric acid, we have 1 hydrogen and 1 chlorine. Okay, so now we focus on our reaction coefficients, and we identify the elements that are not balanced. I guess the short answer would be everything. So we really can just pick any atom of any element to start with. So what element do you want to start with? Keeping in mind, we prefer to balance elements that are found in the least number of compounds first. So the least number of compounds. Silicon, sure. We have 4 silicons on the left. So 1 times what would give us 4 silicons? What coefficient do we guess? 1 times what would give us the 4 silicons on each side? 1 times what is equal to 4? 4, yep. Now make sure to apply your coefficient to all of your atoms. So we get 8 hydrogens and 8 chlorines. Perfect. Now, continuing on, what element do you want to balance next? What element do you want to balance next? What element is found in the least number of compounds? Any particular inclination? There's no wrong answer. We can technically start from and continue this process from any element we want. Which element do we want to balance next as a class? Chlorine, sure. Okay, so looking at chlorine, we have 8 chlorines on the left, so we want 8 chlorines on the right. So 1 times what would give us 8 chlorines? What coefficient do we guess for hydrochloric acid? 8, yep. So we have 8 hydrogens and 8. We have 8 hydrogens and 8 chlorines, okay. Now what element do we want to balance? What's the next element on our list that we want to balance? Oxygen, sure. We have 4 oxygens on the right. We want 4 oxygens on the left. So 1 times what would give us 4? 1 times what would give us 4? 4, yep. So that in turn gives us 8 hydrogens and 4 oxygens. Okay, so we're going to put in our makeshift coefficients. We're not 100% sure about them just yet. And now what we're going to do, and this is really important, is we're going to add together all of our atoms of each element on the left and right-hand side of our chemical equation to write out our total. So in total, we have 16 hydrogens, 4 silicons, and 4 oxygens on the left. And we have 16, because 8 plus 8 is 16, hydrogens, 4 silicons, 4 oxygens, and 8 chlorines as well on each side. I'm just reading off from my total atoms from each of my reactants and products. And as I can clearly see, my number of atoms of each element are balanced in this chemical equation. So we now have a complete balanced chemical equation, and we've verified that this equation is balanced. Does that make sense to everyone? Any questions on this example? Okay, so let's continue on and let's continue. I left an extra table in the notes just in case you needed more space. Now we're going to talk and introduce this next idea of writing chemical reactions from text. So there are some key words that you need to pay attention to when you hear a description of a chemical reaction or you read a description of a chemical reaction in order to correctly draw out the chemical equation. So first, react to give to yield, that's an arrow. And is a plus, reacts with is a plus. So these words are used to convey symbols in the chemical equation. Upon heating, we have the delta symbol, catalyzed by using a blank catalyst. That signifies that you need to put a catalyst above the reaction arrow. Now, just as a refresher, of course, we can get the formulas of ionic and covalent compounds using nomenclature rules. But let's review how to write the formulas of elements, as this is what commonly trips students up on these sorts of problems. And it often leads to, if you don't have the correct formula, you can't really balance an equation effectively. So elements can be atomic or molecular. As we discussed, our atomic elements are our metals and noble gases, while our molecular elements are our nonmetals and our metalloids. So an example of an atomic element would be, for example, sodium. So if someone says the word sodium in a description of a chemical reaction, they're referring to Na, solid. Noble gases would be Ne, like for example, neon, which is an atomic gas. Would someone like to give another example of an atomic element? Would someone like to give another example of an atomic element? Would someone like to try, yep, Li for lithium. Good, good. Okay. Our molecular elements are primarily nonmetals and metalloids. Your diatomic elements, which have two atoms, are your halogens, oxygen, nitrogen, and hydrogen. So for example, chlorine is Cl2. Oxygen, when someone says oxygen in the context of a chemical reaction, they're describing O2. Now, there are only two polyatomic elements. These are sulfur and phosphorus. So S8 would be sulfur and P4 would be phosphorus. And both of them are solids. Now, the reason why we develop this skill of writing the formulas of elements is because if I say in a chemical equation, for example, phosphorus and oxygen react, you need to know how to convert these word phrases into equations. And you need to know the nomenclature rules in order to do that. So let's talk about how am I writing these state symbols? I'm writing them out, but what is the logic behind that? So the physical states of elements and compounds. So the state symbol indicates the physical state of each substance. S solid, L liquid, G gas, AQ aqueous, okay? Metals, most of your metals are solids. The only exception is mercury, where mercury is a liquid. I always like to remember that because mercury is found in these mercury thermometers. Now, for your nonmetals, your noble gases, hydrogen, nitrogen, oxygen, fluorine, and chlorine are gases. So, for example, hydrogen would be H2 gas, fluorine would be F2 gas, chlorine would be Cl2 gas. Nitrogen and oxygen, that's easy to memorize because we breathe them in. They're principal components of air. In the air we breathe. Fluorine and chlorine, I remember just because they're infamous, really dangerous gases to handle. And hydrogen, because it's often the bubbles that you see in hydrogen generating reactions. However you want to integrate this information is up to your preference. I always like to mention these short little pieces of information to help you relate these facts to what we've seen already. Bromine is a liquid. It's not a very fun liquid to work with. It's very dense, it's quite toxic, and it fumes like crazy. Bromine is the only liquid non-metal. In general, most other metals and most other non-metal and metalloid elements are solids. So for example, iodine would be a solid. So that's our elements. Now let's talk a little bit about covalent compounds and ionic compounds, and let's talk a little bit about how the physical state is described for covalent compounds. Now, just to be clear, we don't have any inherent tools to predict the physical state of a covalent compound. However, often in the reaction description, the physical state of a covalent compound is given in the chemical reaction description. So for example, we'd say liquid ethanol. So then, what state symbol do I put behind ethanol? What state symbol do I put behind ethanol? If it's liquid ethanol, what state symbol do I put? Liquid, yep. Carbon monoxide gas, so carbon monoxide is CO. And what state symbol would I put if I have carbon monoxide gas? Gas, yep. So not too bad. So let's take a look at ionic compounds and acids. So we already know that soluble ionic compounds and strong acids dissociate to give their component ions in solution. We looked last chapter at sodium sulfide, and we know that the moment we put sodium sulfide in water, it breaks down into sodium plus and S2 minus aqueous. So compounds dissolved in water are denoted by the aqueous symbol. So in general, if you have a soluble ionic compound, a soluble covalent compound, or any acid, you're almost always going to be denoting them with an aqueous symbol if they're in an aqueous solution, if there's any water present. Anytime you have a solution of a compound in water, that indicates an aqueous symbol. So for example, if we have a solution of sodium chloride, we'd write this as NaCl aqueous. A solution of glucose, we'd write the formula for the glucose, and then we'd put the aqueous symbol. Does this make sense so far to everyone? If we have, for example, a solution of acetic acid, so acetic acid is CH3CO2H, again, we put the aqueous symbol because it's a soluble acid. Okay, so now that we have this idea set up, so if it's dissolved in water, we put an aqueous symbol. Let's talk about insoluble compounds. So insoluble compounds are denoted by a solid, liquid, or gas symbol, and insoluble compounds do not dissociate. So a relative of insoluble compounds are immiscible compounds. Immiscible, not mixable, they're denoted by a liquid symbol. So for example, if you try to mix oil and water, or if you try to mix a non-polar molecule such as hexanes with a polar molecule such as water, these liquids are immiscible and do not mix. So then, if hexanes is immiscible, what state symbol do I put? What state symbol do I put for hexanes if it's immiscible? It does not dissolve in water. So immiscible specifically refers to what state of matter? Liquid, yep. Miscibility refers to how readily liquids can mix together to form a homogeneous solution. So immiscible is in immiscible liquids are indicated by the liquid symbol. Continuing on, another key word that you'll need to be familiar with is the keyword of a precipitate. A precipitate is a solid formed from a chemical reaction. More specifically, a precipitate is an insoluble ionic compound. Precipitates are indicated with a solid symbol S. So for example, a precipitate of silver chloride would be AgClS. Many reactions that we're going to study in this section and many reactions that you may see in the coming laboratories are precipitation reactions. We saw this with our calcium carbonate laboratory approximately a week ago. Any questions? So continuing on, most gases are insoluble in aqueous solution, so we put the gas symbol. So for example, if a reaction makes nitrogen, we'd write it as nitrogen gas. The nitrogen doesn't dissolve substantially in water. Most pure elements are insoluble in aqueous solutions. So if you're dealing with a pure element, you simply write the state symbol for that element at room temperature. So for example, we could do oxygen gas, copper solid, aluminum solid. So anytime you're dealing with a pure element, just write the formula and the state symbol for that pure element at room temperature. Does this make sense so far to everyone? Does this make sense so far? Any questions so far? So not too bad. We're just getting the particulars down to writing the state symbols. And the next chapter that we're going to cover focuses intensely on whether or not you put an aqueous symbol, just as a preview. Okay, so now that we have all these rules established, let's try to work through the following problem together. And let's start by writing out an unbalanced chemical equation with the correct formulas and physical states. Then, once we have that established, we're going to count the number of atoms of each element in the reactants and products. So I'm going to need everyone to help me out here. Carbon monoxide. What formula do I write for carbon monoxide? This is, so we see the mono prefix, so that tells us immediately we're dealing with covalent nomenclature. So I already see in the chat, carbon monoxide is CO. We know in the problem that it's a gas because I say it's a gas. Hydrogen, what's the formula of hydrogen? What's the formula of hydrogen? H2, yep. And hydrogen itself is a gas at room temperature. React, to give. React, to give. What does that mean? What do I draw? When you see the words react, to give, what does that tell me? What do I draw? An arrow, yep. Okay. This and tells us I need to write a plus. And we in turn generate a liquid with the formula CH3OH. So I write my formula CH3OH, otherwise known as methanol, and I put a liquid symbol. Okay, so now that I have this all established, what we're going to do next is we're going to count the atoms of each element. So I have one carbon, one oxygen, and two hydrogens on the left. I have one carbon, one oxygen, and four hydrogens on the right. Let me move this 2 over just a little bit. So that way we have space for the next part. So, which elements are not balanced? Which elements are not balanced in this equation?
Hydrogen?
What was that?
Hydrogen?
Yep, exactly right. So hydrogen is unbalanced. We have 2 on the left and 4 on the right. So what times 2 would give us 4 hydrogens? What coefficient do we put in front of hydrogen?
2.
2, exactly. Perfect. So now we have all of our atoms of each element balanced, and we have our complete balanced chemical equation. Not too bad, right? The only thing that I want to caution on these sorts of problems is if we don't have the formulas, we're stuck. So really make sure you review your nomenclature. Okay? As this is really critical to your success in these later problems. So continuing on, we balance this equation pretty quickly following the same procedure. I had extra space in case students wanted to go through the procedure step by step and rewrite the equation each time, but that was a pretty fast balancing act. I'd like us now to take a look at the following example and to try to apply what we've learned to write and balance the following chemical equation. And I'll give everyone about 5 to 6 minutes to balance this equation because you need to be able to write all your formulas correctly in order to proceed. So we'll discuss this example in about 5 to 6 minutes. Don't be shy to submit your responses in the chat or ask questions in the chat. And in terms of when we're going to discuss nomenclature, I'll give everyone about 3 minutes to look over this problem. And then in 3 minutes, we'll be writing out the formulas. So that way, if you're stuck on the formulas, you can at least see the logic behind and review nomenclature rules and then try to balance the equation. So let's spend about 3 minutes initially writing the formulas and 6 minutes total trying to balance the equation. And don't be shy to message your proposed balanced chemical equation into the chat as a public or private message. In about 2 minutes, we'll focus on writing out the basic formulas, writing out our skeleton. And the responses I see in the chat so far look perfect so far. We'll continue to work through this problem and we'll discuss the nomenclature in about another minute and a half. So let's focus on writing out the formulas. So copper 2 chloride. So that 2 signifies the charge. So we have copper 2 plus, chloride is Cl minus. So we cross the charges and that gives us CuCl2. We see the word solution, so we put the aqueous symbol. Would someone like to volunteer? What should I write for sodium sulfide? Sodium sulfide. What formula should I write for sodium sulfide? And don't be shy to type it in the chat or unmute and state the response verbally. What should I write for sodium sulfide? Na2S, exactly right. Thank you. And since it's a solution, we put the aqueous symbol. Okay. It yields solid copper 2 sulfide. So we have copper 2 plus, S2 minus. We cross the charges. And I'd like to ask everyone, what is the formula of copper 2 sulfide? And be a little careful about this. What is the formula of copper 2 sulfide? And don't be shy to share it in the chat. CuS, exactly. Be very careful that you simplify your subscripts. That can cause a lot of problems if you try to balance an equation. Sodium chloride is NaCl. Aqueous. Okay, so now that we have our rough equation, I've already seen a reasonable pool of responses so far for the balanced equation. So I feel comfortable proceeding. So counting our atoms, we have, let me do it in the correct color so that way we have some consistency. So I have 1 copper and 2 chlorines, and I have 2 sodiums and 1 sulfur. For copper sulfide, I have 1 copper and 1 sulfur. And in sodium chloride, I have 1 sodium and 1 chlorine. So just because your reactants are in solution doesn't necessarily mean your products will be aqueous. It depends on their solubility. And we'll talk about the solubility rules in the later half of this chapter / next chapter. So copper sulfide is actually not soluble. It doesn't dissolve in water, and that's why it gets the solid symbol. Essentially, some compounds are soluble, other compounds are not. And for now, I'm telling you which compounds are soluble and insoluble, but in the later portion of this chapter, we will develop the rules to assign solubility and determine whether something gets the aqueous symbol or the solid symbol. Did that answer your question? Perfect. So looking at our number of atoms of each element, we see that sodium and chlorine are not balanced. So let's start with sodium. 1 times what would give us 2 sodium atoms and 2 chlorine atoms? 1 times what would give us 2? 1 times what would give us 2?
2.
2, yep. Perfect. So now we have 2 sodiums. Let me write that a little more cleanly. So we have 2 sodiums, 2 chlorines. Copper and sulfur are balanced, so we have a complete balanced chemical equation. So let's just rewrite our balanced chemical equation. So overall, not too bad. If you're comfortable with your nomenclature rules will really save you in this chapter for sure. So here's our complete balanced equation, and let's put a check mark next to it. Okay, that's wonderful. So let's now do some more examples. Let's do some more examples. If there aren't any questions, just I'll pause for the opportunity to ask questions. As I don't see any questions verbally or in the chat, let's keep moving on. Let's keep applying what we've learned. And this time I'll be providing you another guided example and just reviewing our problem solving process. So we have a solution of lead 2 nitrate and a solution of sodium chloride are mixed, yielding a solution of sodium nitrate and a solid precipitate of lead chloride. Okay, so lead 2 nitrate. So I have lead 2 plus and nitrate is NO3 minus. I cross my charges and that gives me Pb NO3 2. It's a solution, so I put the aqueous symbol. Sodium chloride, it's just table salt, NaCl aqueous. Sodium nitrate, we have Na plus, NO3 minus. We cross our charges and that gives us NaNO3 aqueous. Lead chloride, we have Pb2 plus, Cl minus. We cross our charges and that in turn gives us PbCl2. It's a precipitate. So what symbol do I put? What state symbol do I put for a precipitate? What state symbol do I put for a precipitate?
Solid?
Yep, exactly right, solid. Solid precipitate, I said in the problem solid precipitate, and that's a bit of a, it's a bit redundant, but in general, whenever you hear the word precipitate, think solid. Okay, so now that we have our unbalanced chemical equation, so let's just write that out right here. So now let's count the atoms of each element. So I have 1 lead, 2 nitrogen, and 6 oxygen. If you notice that when I solve these problems, I'm using the table method. I'm just not drawing out a giant fancy table. That's why I like the table method, because it can be pared down and made a little bit more user-friendly. Okay, so now we're just counting the atoms of each element, just reading off from the chemical formula. Okay, so looking at this equation, which elements are not balanced? Which elements are not balanced? Which elements are not balanced? Oxygen. Yeah, now for this equation, this type of equation is known as an ionic equation. And you can think about balancing ionic equations in terms of ions. So you can say that we have 2 nitrate ions in this above example. Well, in the species on the right, we just have 1 nitrate ion. So if we want to balance, thinking about this ionic equation in terms of ions, 1 times what would give us 2 nitrate ions? Or in other words, 1 times what would give us 2 nitrogens? What should we guess for our coefficient? What coefficient would we need? 1 times what would give us 2? 1 times what gives us 2?
Mhm.
2, yep. So we plug in a coefficient of 2. So we have 2 nitrogens, 6 oxygens, and 2 sodiums. Okay, now sodium is unbalanced. So 1 times what would give us 2 sodiums? 1 times what gives us 2? 2, yep. So we have 2 sodiums and 2 chlorines. Lead's balanced, chlorine's balanced, sodium's balanced, nitrogen and oxygen are balanced. If you think about things in terms of ions, it can certainly reduce the amount of bookwork that you have to do for these ionic equations. So let's just rewrite this equation so that we have our complete final equation. So here's our complete balanced equation. And in the later pages, I left some space if you wanted to use the table method. So if you want to try using the table method, there's space in the notes for you to reattempt the problem. Now, let's take a look at the following example, and I provided a table below just to help everyone organize their thoughts. And I'd like you to attempt balancing the following chemical equation after writing out the formulas from the names of each of these compounds. So let's take about 3 minutes and let's try to write the formulas of all of these compounds. And if you're feeling ambitious, you can also try to balance this equation. So we'll spend about 6 minutes total on this problem, but after 3 minutes, we'll come together and we'll discuss nomenclature, just so that way we're not stuck writing out the names, and we want to make sure that our formulas are correct, so that way we can balance the equation effectively. And we'll discuss the nomenclature and write out the formulas for each of these compounds in about another minute and a half. The responses I see in the chat, I would double check to make sure potassium is balanced, but most of the other coefficient, I would double check that potassium and barium are balanced in the response that I just saw in the chat. Let's try to get a few more responses in the chat. And if you have any proposed formulas for these names, don't be shy to message them in the chat or unmute and propose your responses verbally. The coefficients that I just saw in the chat look good. And we'll draw out the formulas in about another minute, just so that way everyone has the opportunity to try to recall their nomenclature rules, apply these nomenclature rules to write the formula, as this is really the starting point for when you can start handling these courses and handling this specific chapter. So the balanced equation that I just received in the chat looks perfect so far. Yep, the chemical equation that I just see in the chat looks perfect. So let's now discuss and apply our nomenclature rules. So barium hydroxide, barium adopts a 2+ charge. Hydroxide, would someone like to tell me what is the formula of hydroxide? What is hydroxide?
OH negative.
Yep, it's a polyatomic ion, OH minus. We cross our charges, and that in turn gives us barium hydroxide. It's a solution, so it gets the aqueous symbol. Potassium sulfate, potassium sulfate is potassium plus. Would someone like to provide the formula for sulfate? Notice you have to be really particular here. It's the ATE ending. So what's the formula?
-2.
Yep, SO4 2 minus. We cross our charges, and that gives us K2SO4. It's a solution, so it's aqueous. Potassium hydroxide, K plus OH minus. We cross our charges. That gives us KOH, aqueous. And barium sulfate precipitate. Fun fact, barium sulfate is an old school imaging agent that's used for MRI imaging resolution. And it's one of the few non-toxic ionic compounds of barium. Because it's so insoluble, even in acid. Okay, so now that we have our balanced equation, let's take about another minute and a half and let's try to, now that we have our unbalanced equation, let's take another minute and a half and try to balance this equation. And if you want, you can use the provided table below to count the atoms of each element on the reactant and product side and attempt to adjust the coefficients. So we'll discuss in about another minute and a half. Let's try to get a few more balanced equations in the chat and we'll discuss momentarily. Okay, so let's discuss balancing this equation. So let's put both of our reactant molecules into our table. If we have a table handy, might as well use it. Though any method that you choose to use to balance chemical equations is perfectly fine as long as it's logically sound. So counting the atoms, we have one barium, we have two oxygens and two hydrogens. We have two potassiums, one sulfur, and four oxygens. And again, I always like when I'm dealing with these ionic equations to bundle my ions together. So you can think of this two oxygen and two hydrogen as two hydroxides. And this will come in handy in a moment because it helps minimize the amount of atom bookkeeping you have to do. In potassium hydroxide, we have one potassium, one oxygen, and one hydrogen. And we can group the oxygen and hydrogen as they're part of hydroxide. In barium sulfate, we have one barium, one sulfur, and four oxygens. And again, we can group the sulfur and oxygens together as sulfate. So now to play a game of guessing coefficients. As you can see, we have one hydrogen on the right and two on the left. So 1 times what would give us two hydrogens? What coefficient do we guess for potassium hydroxide? Sorry. What coefficient do we guess for potassium hydroxide? What coefficient should we have for potassium hydroxide? 2, yep. So that in turn gives us two hydrogens, two oxygens, and two potassiums. So in total, oxygen's balanced, sulfur is balanced, potassium is balanced, barium is balanced. So we're all set. Just one coefficient, that's it. And now we have a complete and balanced chemical equation. Any questions on this example so far? If not, let's continue on. Add an extra table just in case. And let's talk in the last few minutes of today's session about a really nice shortcut. And it's known as half notation. So half notation is most useful when you have a pure element. So remember this criteria. This is really important. When you have a pure element, anytime you have an isolated pure element, half notation will be quite useful. So first and foremost, you balance as many elements as possible by adjusting the whole number coefficients. Okay? In general, you start from the most complex molecules before balancing the isolated elements. Okay, so what do I mean by that? So in N2H4, I have 4 hydrogens. In NH3, I have 3 hydrogens. Okay? So I'm going to use the least common multiple method. So I'm just going to adjust my coefficients. So 4 times 3, we get 12 hydrogens and 6 nitrogens. 3 times 4 gives us 12 hydrogens and 4 nitrogens. N2, we just have 2 nitrogens. So in this case, our chemical equation balanced using the traditional method is completely balanced just with this first least common multiple method. Now, to showcase a little bit about what is happening under the hood per se, what is happening internally and why this least common multiple method works is instead of using the least common multiple method, especially when you have a pure isolated element, instead what you can do as an alternative is you can place fractional reaction coefficients to balance the chemical equation. So for example, if we have 2 nitrogens and 4 hydrogens on the left, and we have 1 nitrogen and 3 hydrogens and 2 nitrogens on the right, instead of being constrained with this idea that we have to have whole number coefficients, instead what we can do is we can guess a fraction. So my question to all of you is 4 times what fraction? 4 times what fraction would give us 3 hydrogens? And a trick to write out your fraction is you put what you have on the bottom and you put what you need on the top. So then, what fraction can I guess? What fraction can I guess for this reaction? What fraction can I guess? 3/4. I need a 3, I have a 4. And you may say, haven't you just made a mess of things? Well, we have, in a sense, that now we have 6/4 nitrogens and 3 hydrogens, okay? Okay, so now we have to play a different game. Now we have to play another guessing game. So 1 nitrogen plus 2 nitrogens times some fraction. We're now going to guess the fraction for nitrogen. So we have 2 nitrogens, and we're going to try to guess the fraction in order to give us equal numbers of nitrogen atoms on each side. So in this case, 2 times what would give us 1/2? Where did I get this 1/2 from? 6/4 minus 1 is equal to 3/2 minus 1, which is 1/2. So 2 times what coefficient would give us 1/2? 2 times what would give us 1/2? So let's set up that equation. 2 times what would give us 1/2? So the trick for this, you put what you want on top, you put what you have on the bottom. So what fractional coefficient should we guess for nitrogen? What fractional coefficient should we guess for nitrogen? What times 2 would give us 1/2? We guess 1/4. Exactly right. Now you may say, well, this seems quite messy. Well, the reason why this half notation method is so useful is because once you have these fractional coefficients, and this is the heart of the least common multiple method, by the way, you then have to take this chemical equation, which has fractional coefficients, and we need to convert it to a proper balanced equation. And to do that, we multiply all of our reaction coefficients by the least common denominator. So what is the number on the bottom? What is the number on the bottom? What should we multiply all these fractions by to get rid of our denominator? So we'd multiply everything by 4, and that in turn gives us 3N2H4 gas leads to 4NH3 gas plus N2 gas. So the least common multiple method that you've been using throughout this chapter is built on half notation shortcuts. Now, half notation is invaluable for balancing equations in which you have an isolated element. Now, in this case, the least common multiple method works quite well. But in later problems, as we'll see, it becomes quite convenient to, instead of manually using whole number coefficients, it becomes substantially easier to use a fractional coefficient. And to showcase this, let's look at another example. But just to check, are there any questions so far on this example? If not, before we close out, let's look at the following equation where we're asked to balance the following equation. Anytime you see a reaction involving oxygen, these are typically known as combustion reactions. These are the best case scenario for this half notation method. So let's write out each of our formulas. And counting atoms, I have 4 phosphorus and 2 oxygens on the left, and I have 1 phosphorus and 3 oxygens on the right. So then, what coefficient do I need to guess in front of PO3 in order to get 4 phosphorus? What coefficient do I need to guess? What coefficient should I guess in order to get 4 phosphorus? 4, yep. So that in turn gives us 4 phosphorus and 12 oxygens. Okay. And now if we have 2 oxygens on the left, 2 times what would give us 12 oxygens? What coefficient should we guess for oxygen? 6. Okay. Let's try to apply half notation to another example. Let's try to apply half notation to another example. So I'd like you to take a look at the following problem, and I'd like you to try to balance the following equation using any method. You can use the least common multiple method, or you can use the half notation method. And this one's pretty fast to balance, so we'll discuss this example in about 1 to 2 minutes. And don't be shy to message your balanced equation for this example into the chat. And the responses I'm seeing look great so far. Let's try to get a few more responses and then we'll discuss in about another minute. Okay, so let's discuss this example. So we have 2 nitrogens and 2 oxygens on the left-hand side, and we have 2 nitrogens and 5 oxygens on the right-hand side. Now, instead of just balancing using the least common multiple method, let's try to play a guessing game and figure out 2 times what would give us 5 oxygens. 2 times what fraction would give us 5? What fraction should we guess? What fraction should we guess? If we're using half notation, what fraction would allow us to balance this equation? 5 over 2, exactly right. Okay, so now we have N2 gas plus 5 over 2 O2 gas leads to N2O5 gas. And now what we're going to do is we're going to multiply all of our coefficients by a whole number. And what whole number should we multiply by? What is the common whole number in our denominator? What should we multiply all of our coefficients by to get rid of this fraction? To get a true balanced equation with whole number coefficients. What should I multiply all of my coefficients by? If I want to get rid of this number on the bottom, I'd multiply everything by 2. And that in turn gives us 2N2 plus 5O2 leads to 2N2O5 gas. So as we can see, the half notation method can introduce and improve your efficiency in balancing reactions that contain isolated elements. This is just another tool in your toolbox. You can choose to use whatever method of balancing equations that we've talked about this session that works best for you. So we'll take, that's the end of the first lecture for today. We'll take a quick 45-minute break, and then we'll resume in laboratory at 12:45. So I'll see everyone in laboratory, and we'll continue on the lecture and talk about calculations in the laboratory section.